Okay, our next speaker is from the Heinrich-Hertz-Institute in Germany. The speaker's name is Roland Bartmann, and the name of the talk is Flat Autostereoscopic 3D Display with Enhanced Resolution using a Static Color Filter Barrier.
Hello, everyone. I will start with a short introduction to the Fraunhofer Society. Not every one of you will know them, I think. There are about 60 institutes in Germany and about 20,000 scientists all over the world. And it's maybe the biggest research organization in Europe. But the institute I came from is the HHI in Berlin, and it has a long history. It was founded in 1928, and it's famous for telecommunication research and in fiber optical transmission and video coding. Okay, let's go on. I'm from the Vision and Imaging Technology department, so we are dealing with 3D analysis and synthesis methods for different application fields. For instance, medicine and media. And one part is deals with capture systems and display systems. Whoops. Yeah, I will tell you more about. This is our last prototype, an 5K 27-inch autostereoscopic display with lenticular, image splitter, and two cameras for position tracking of the observer. But that's not the topic of this talk. And the topic of this talk is color filter splitter. And here is a short overview about the talk. I will start with the 3D displays, then go on to the filter model that lies behind, and tell you something about the simulation. It's very important. This talk is more theoretically. So we haven't built an appropriate prototype with this proposed color filters yet. And so we have done some determination of luminance and crosstalk to predict the possible quality of such solution. And the results concerning the illumination I will show you. And at least we have some design rules for such display devices. Okay, so let's start with the 3D displays, commonly known for everyone here, I think. We are dealing with the autostereoscopic ones, glassless displays, flat panel-based, here like you can see here. And what's the question about? You need some kind of optical separator or image splitter to get the different use for the observing people. And it's nice to have multi-view, of course, but that's other topic. So I would show you something regarding color filter, the color filter approach. So what's the important parameters? If you want to separate the images with color filters, you need narrow band wavelength selective filters. to get a good separation for the colors. Here and in the right image, you can see this image splitter with the RGB matrix. And important parameters, of course, are the 3D resolution you get from such device, the brightness, and of course, we have to minimize the crosstalk. So the input parameters are the filter stripe of the barrier. That's, of course, the design parameter. And we put this together in our simulation and can do such automatic design evaluation. Here on the right side are two example pictures of our simulation. Here's the display system again with the image plane and the image splitter. And here you can see some color-coded viewing zones, and this bubble here is the observer. And this is a sample for a measurement. Of course, with this simulation software, we can model different barriers, parallax barriers, and also lenticular ones for this prototype I showed you before, and the wavelength-selective I talk about here. And important thing is we have some implementation of automatic design search, so we can input a range of parameters, and then the software will search for the best solution for itself. So this is a short animation of the principle. Here, this is the RGB pixel plane of the LCD, and this is the color filter, the RGB color filter. And it is tilted, and you can see how the stripes, the perceived stripes, are moving in front of. Yeah. And yeah, it's only was a mere magnification. It's only a part of the whole system. Okay, so how is the model? You saw this animation, and this is the top view of the system. There is the image splitter, the pixel plane, and here's the color filter image splitter. And we have here a two-view system coded by numbers 1 and 2, and the different colors for the subpixels. And here are the outgoing rays, and they only transmit through the filter cells with the same color. And here is the observer zone, and important, of course, is this width here and the separation of the colors. So there are the parameters. Here the subpixel width and the viewing width, and the parameters of the image barrier and the distance. And that's the parameter to calculate. And of course, the distance here, this is the input parameter. And there are some linear equations for the observing zone. Here we have the eyes of the observer, and we like to have this. We want to have this 65 millimeters IPD, and of course there's another zone here. This is caused by the width of the subpixels, and it's an important parameter because we like to have a good separation of the views here, 1 and 2, and this is here, for instance, the T parameter. Okay, what we can do? We have some relations here. The zone width relates to the views, and this immersive zone, radiation zone from the subpixel, relates to the filter gaps, especially to the gap S here, that's between the colored stripes. And now I will tell a little bit more about it. So let's talk about the pattern and gaps. And this is here an example of the simulation results we've got. On the left side, you can see the frontal view of the colored image splitter plane, and it's like in the short animation. So you can see here the different colored stripes, and what's the difference between the both results? On the left side there is no horizontal gap, and on the right side there is a 25% gap. So I will explain to you why we got this. If we look at luminance distribution in the observing zone, we can take a single row of this projected plane, and then we get this nasty peaks here for the no gap variant, and with the gap we have an homogenized luminance plateau. So this was calculated for 6,500 millimeters common distance. So again, here are the eyes, and the peaks are dropping down with the gap. And if we calculate this for more than one row, the gap, the peaks will vanish, and with the gaps we have this luminance, this decrease, but wider plateau zones. So, what's the difference? Again, here is a magnified area of the no-gap version. And what you can see here, the summation of the colors in the rows is different. So here you have 3 subpixels, and here 4.2 and 4.8, and this will cause luminance fluctuations we do not want. And if we look at the gap version, then suddenly we get the same sum of the pixel colors, and that's the way we come to an uniform light distribution. Okay. But it's only for the color filters, so we have to compare it with common barriers, the white and black barriers. You can see here the luminance plots of the white and black barriers, dependent of the relation of the black and white stripes. So with the 1 to 5 barrier, there is not much luminance left. But the black and white barrier related to our color filter approach is the 1 to 3 barrier. Yeah, you can see here. Okay. What's the difference between these 2 barrier types? If you look at the crosstalk at the minimum range, then we will get with the color filter approach an increase in the plateau width of about 10 millimeters or so, and that's a lot, I think. Okay. We have calculated different parameters in our simulation, and there are different possible solutions for color filters. So that's the A variant with no gap. Then we have a gap, this 25% gap, but we can also change the order of the colors. Yeah, here from B to C, we change the order of the colors, and so we get better illumination uniformity of the panel. And also there is the slant angle of the color filter stripes, and we can altering that angle, and then with a lower angle we will get the solution D, and it's really nice distributed. The colors are really nice distributed here, and you will get a good white balance. But we have to say maybe the moving space the observer gets will be restricted, more restricted for this solution here. Okay. And so at last, I will come to the design rules for such an approach and color filter display. At first, one can get with the color filters up to 1/3 of the source luminance through the display, and that's more in comparison to the black-white barriers. And we have to keep in mind to fabricate such filters, there are gaps needed. So our approach gives you a possibility to use the gaps wisely, and we give the designer the possibility to homogenize the radiation characteristics of the display and eliminate the fluctuations, the luminance fluctuations, because of the homogeneous distribution. Okay, that's all. Thank you.